bottom and your thumb points towards magnetic north. Okay, so here is your north pole, here is the south pole. Nice. Okay, so that's a quick review on what we did last day, right? So my question now is just to go back to what we were talking about. Whenever we have two magnetic fields interacting, whenever we have two magnetic fields interacting, like you bring two bar magnets together, what's happened? If you bring two bar magnets together, they could either what? Attract or repel. So basically a force is experienced. Okay, so what do you think will happen? What do you think will happen if I take a magnet, a north and a south pole, and I bring a current carrying conductor in between it? What do you think will happen to that conductor? Probably experience a force. Yeah, because remember, the conductor has a magnetic field, right? And the magnet has a magnetic field. So somehow they would interact, right? So that is going to bring us, to what we call Fleming's left-hand rule. Okay, but I want to show you it. I want to show you a simulation on it first. Okay. Hello. Don't worry. I'm coming home. I'll take a picture of it and I will try and get started. Okay, I'm going. All right, so just pull it up and take big picture, real heavy, yeah? Okay, all right, okay. All right, fine. All right, so watch this here. Let's see. Online, you'll see that simulation there. All right, nice. How do I take off those things, sorry? There you go. Turn them up, boy. Yeah, boy. Get upside down. Yeah. All right. I want you to kind of see. All right. I don't know if you all seen it so good there. I'll try to get the angles so that you will see. You all seen the magnet? You all seen the magnet there? The red and the blue? Right. And in between, there's a current carrying conductor. That's a little black line there. Yeah? All right. So what's going to happen here when I press play? See what happened there? It experienced the upward force. You see that? It coming back in and going back up again. So basically, once it enters there, it experiences an upward force. You're okay with that? So the conductor experiencing a force because of the interaction of its magnetic field with the magnetic field of the magnet. That makes sense, Amara? But we need to be able to work out the direction of that force. All right? I'm going to show you one more simulation. There's a next simulation that shows you the field lines. There's one in Java too, but I don't know. That's not. It's not a video. line is it? No. Anyway, I'll show you online then. All right, so here's all we have, right? All right, and there's a Fleming's left arm rule. I'll give you a little note just now, but I want to make sure you understand how it works. So if I give you a magnetic field, north to south, magnetic fields always move this way, right? North to south. If I bring a conductor in the middle here, right? That conductor has a magnetic field around it, right? So remember, dot means what? Dot means out. So there is a magnetic field going counterclockwise here. Okay? Those two magnetic fields will interact. And as a result of the interacting, it causes it to move upward or downward. Right? Remember, when we have two magnets, a north and a south pole, right? And they interact and they come into each other. If I had a north and a north, they push away from each other, right? Right. So if you watch here, these field lines going to interact somehow. This arrow going with this arrow going against this arrow. So it will interact somewhere and it won't interact somewhere. So somewhere to have attraction, somewhere there will be repulsion. Let's see what will happen, right? And there was a guy named Fleming. He investigated the behavior of that conductor, right? And he came up with this rule. You have a thumb at right angles to your first finger, and then your first finger at right angles to both of them. So it looks like this, right? Thumb, your first finger, and your middle finger. Okay? And talk about the next two. Okay? You don't need these, you just need these three here. Okay? The thumb is the direction of the force. Your first finger is the direction of the magnetic field. And your middle finger is the direction of current. Okay? So you have these three fingers, and these three fingers, all you're doing, you are not moving these fingers. Anything that we're gonna do, your fingers staying like this, and you just move in your hand. Right? So if you want, you can cut this off and just rotate it. Right? You're not moving your fingers. And some of you all, when you're moving it, your fingers just kind of come out like that. Right? You want to keep your hand as sturdy as possible. Okay? So I'm going to show you how it works. Trying to figure this out. Your hand will rotate and it will tell you what direction the force is. Okay? So let's start first. Magnetic field moving from north to south. So your first finger moving from north to south. That's okay? Your middle finger. This means out or in? Out. Current coming out. Right? So your first finger is magnetic field. Your magnetic field moving north to south. And your middle finger, which is current direction. This means current coming out. And then your thumb will naturally point in the direction of which the force will be on this conductor. So the force is up. You seen that? Yeah? Yeah? Yeah. And here's why that happened. Here's why it went upwards. Online? Are you okay with that then? Right? Here's why. So you have a conductor here, right? Here's what happened. The magnetic field line interact on it. So the magnetic field lines kind of build up underneath here. And on top, there's no interaction. So it kind of pushes it away. Right? What that did is it created a rubber band effect. Right? So you have all the magnetic field lines underneath and nothing on top. What will happen? It'll push it upwards. Right? It'll push it upwards and your force is upwards. Right? So it creates a kind of rubber band effect here. And when all these field lines build up here, push it down. Okay, so this is your Fleming's left hand rule. Okay, head up Fleming's left hand rule. Which classic important? I'll make sure you come to the right class now. Come to the shades. Huh? I will be now sat there. I'm a copy down the fast, which is it's over. You see? All right, so let's do a quick little drawing diagram. I want to give you a note, right? If you could draw the left hand rule, you could draw it one time. This whole thing here. Ready? Ready? Finish. Draw it. This is important to make sure you draw this right, but I want to explain this here. Right? Because if a question asks you to draw the field lines between around the conductor, that's how it will look. Yeah. And you'll understand why the field line is pushing it upwards, right? Okay. So, am I right answer? Finish. Plenty of magnetism is not really, there aren't much calculations in magnetism, it's more theory, right? The calculations come when we do transformers. All right. Yeah. Ready? When the magnetic field under this diagram, you're writing the note. When the magnetic field of the magnet interacts, when the magnetic field of a magnet interacts with the magnetic field of the conductor, a force is exerted. A force is exerted on the conductor. A force is exerted on the conductor due to the buildup of the magnetic fields on one side of the conductor. Due to the buildup of the magnetic fields on one side of the conductor. Oh, what was the heading? Sorry, Fleming's left-hand rule. My marker making it look real bad there. So what is the word on the bottom of the three-finger rule? Current. Magnetic field, current, and force up there. Are you okay there? Alex, are you okay there? All right, nice. Right. I will send you a new timetable when school opens, right? Your class will be Admath is Monday, Wednesday is maths, Friday is physics. And same time 3:30. And Saturday is a new cycle for the phone codes. So if you probably want to join them, or you could join them and get some version as well. Okay, and I will tell you how the topics will run. Okay, and I'm also going to add you all to LMS with all the notes, all the videos, everything for all these subjects. All right. So at any point in time, you want to go back and revise tomorrow, you can go back and watch the videos and revise tomorrow. Do the past papers, do the quizzes. All right. All right. Nice. Full stop. Fleming's left-hand rule is used to determine Fleming's left-hand rule. Don't write the whole word, right? Don't write the whole thing. Right? Fleming's left-hand rule. Fleming's left-hand rule is used to determine the direction of the force on the conductor. Fleming's left-hand rule is used to determine the direction of the force on the conductor. On the conductor. the direction of the force on the conductor. All right, full stop. You're through this already, right? And remember, using your left hand, even if you're right-handed, using your left hand, don't matter. Your left hand you're using for all these rules, right? Okay. So, so Fleming's left hand rule is used to find the direction. So the purpose of this left hand rule is to find the direction of this force, right? And remember, when you're moving it around, do not move your fingers. You're just moving your wrist, so you can turn your page and just adjust it. Okay? And every time you do it relative to the page. So you can draw it on your page, move your hands relative to the page. Okay? Otherwise, you'll get direction wrong. All right? So let's go up here. So I want you to apply Fleming's left hand rule here. Right? I join the poles here for you. South, north. Magnetic fields always move what? From north to south, right? And I'm going to put a X here. Tell me what to put, up or down. Use your rule, tell me up or down. I'll call somebody up and they will get to come and practice it here. Watcha? No class on it, money. You lost it. That's like I know. All right, so I'll find my thing. Right. So I want you to figure it out. Up, down, left, or right. Okay. Use the left hand rule. Tell me up, down, left, or right. And I'll call somebody on the board. Right. Those who messaging online, remember, don't send it to everyone. Just to me alone, right? Up, down, left, or right. I'll call somebody to do it. I'll give you a minute for that. Ready? All right, so let us call Malachi. From Malachi, you reach late, so you reach late. So let us see if you pick up on it. Huh? If not, then but I'm here. I'm here to help you out. Come up here. Left hand rule. Right, so take them out. So you start on that. All right, right, left hand. Right, so but turn us so they can correct you. What are you doing wrong? Right, everything has to be 90 degrees, right?
That can't bend so far.
Right?
Oh,
Right, 90 degrees. That's okay? This hand has to be like that. This is the, this here is the magnetic field direction. This is the, and this thing here is the force. I can't let you on the street now. Right, come. Just come right here. So we direction in magnetic field. Magnetic fields move out. North to south, right? So from this way, right? So your magnetic field moving north to south. That's okay. You see, I just make him shift. So take a book and then shift the book around. And X means what? In or out? X means in, right? So watch it here. Now it's lining up. X is in, north to south. So your thumb is up. So the forces upwards. I seen everybody got downwards there. Huh?
It's staying like this, so you got
No, X means what?
And
In. So your current is in. What's your hand? The current going in, the magnetic field is the first finger going that way. So the force going upwards. That's okay? So the answer is upwards. Right, yeah. Well, it's based on how these things behave. I'm gonna give you some more now. Right? So what's it? Right, so watch it here. Again, current going in. So my middle finger going inwards. Magnetic field moving north to south. So everything have to go according to this, right? So X is in, magnetic field north to south, so therefore the forces upwards. Aiden, Katrina, are you okay there? Everybody okay there? Where you going? You watching this or no? Where you going? Number 3. Let me just. Try this here. Use the rule, although you can watch it and figure it out. Where the photo? Try this one, yeah? Yeah, wait, that's your one next to that's all.
I think so. Like,
And that's it, not that. And you see what Piano did? Piano drew the P lines one time. That's excellent. I didn't ask Wade, but that's excellent. The drew the P lines one time. Right? We had to fix it. All right. This one here. The P lines will be on top pushing the button. Very good. Like that piano. Right, online message here, up, down, left, right. Sebastian, did I answer your question? Oh, you didn't see the X, okay. Sebastian, you okay there? Oh, for the first one, yeah. So the first one, the X means the current going in once, right? Right, who want to come and try this one? Pete? What you get for this one, Pete? All right, look, piano coming. John Wick, boy. Right, left hand rule, right, he lines up nice. Current going in. Someone wrong there. Magnetic field moving how? The south. So this finger have to point next week. Alright.
yeah.
Perfect. He rotated. Magnetic field north to south. Current going in. Forces downwards. Nice. So the answer is downward. Very good. Forces downward. Right, pushing it downward. Very good. 2 more. As a dot, right? As a dot. I'll draw the X a little bit larger so you will see it. Workout number 4. Tell me up, down, left, or right. I'll pick somebody else. Wait, after this one is yours. And between you and Melon. Tap on you, take your time. Up, down, left, or right. All you have to do is figure out this will not be part of the Take your time. Up, down, left or right. What? Carbon. Right, complete. You have Malachi, I mean, you and Jacob is somewhere. Right, let's see. So what speed you got lines up here? Magnetic field moving north to south, good. Current coming out. So therefore the force is to the right. Very good. Very good. Quick question. How will the field lines look? Right, and where will most of the field lines be? Left side or right side? Okay, any questions online? Jose? Hi, Charan, any questions? Adele? Selena? Baraj, are you okay there? So how you get right? Okay, check it again, just to make sure. Okay, I'm gonna just make sure. Right, so there's a dot, right? So current coming out. North to south means it coming down, right? So I'm taking my left hand, right? Taking my left hand, magnetic field going north to south, right? So I'm pointing it downwards, first finger pointing downwards, right? The current coming out, so therefore my middle finger pointing outwards. Okay, middle finger pointed out to the whiteboard, so therefore my thumb point to the well to the right. All right. All right. So 1, 2, 3, 4. Last one. Anybody confused? Sebastian? Jose? Are you okay now? Right. Even if I don't call your name, let me know if you all get in trouble, right? Last one. You see the X there? There's an X, right? Online, there's an X, right? Work it out quick. That's the last one. And then we're going to learn why we're doing this law, right? So if you lines as well, meet with a pencil. Okay, so you see that, right? Okay, nice.
Yes, that's what we. Yeah.
All right, let's see. Current going in, magnetic field, north to south, so the force is to the right towards me. The force is towards me, which is the right. Right, so just like this. Okay. I saw somebody get it wrong, so let's squeeze in one more. Last one. Last one there. Let's see if we can all get this one right, because I saw somebody get this last one here wrong. Adele, make sure you're using your left hand, right? Aidan, make sure you're moving your left hand. Shannon. Right, try it one last time. Shannon, message your answer. Adele, so to make sure you all get in this, right? Remember, you're using your left hand. Right, last minute. Right, come on, do this one for me on the board. Malini.
So how we get the money?
This man take all the money and we can't find it now.
Yeah,
Which direction? Right, so Melanie said to the left. Good job. Right? So good. Why we learn this for? Why did we learn Fleming's left-hand rule? Right? What takes current and magnetic fields and gives it a force? What type of electronic device constantly gives it a force? Huh? Now, that's giving current. Right? What does give you a force all the time? A what? Huh? A generator giving current. What's the opposite of a generator? Huh? Conductor, nah. A radiator, nah.
That's also it.
Well, that's it.
M. A motor. A motor.
I said that.
Right? So a motor takes electrical energy and gives it magnet and gives you a force. So a motor gives it that constant mechanical energy. So this here is the fundamentals behind a motor. Okay? Online, are you okay with that? So we're going to investigate how a simple DC motor will work. All right, Alex, are you okay with that? Cameron? So we're going to take a look at how a simple DC motor will work. All right. Firstly, I like to show you a simulation so you know what's going on. Jaya here. Maria here. No, Ricardo didn't come either. Jacob Malachi. All right, nice. Let's take a look at our simulation, right? The only problem here is that we have to be able to explain this in words, right? And I'll show you a nice way to remember it. Right, so you could look for a simple DC motor simulation, right? Java has a good one. Physics has a good one. Hold on, eh? Let's see which one. Remember which one better. Okay. All right, let's take a look at this one here. So what is here? What do we have here? Right? What do we have here? So here we have a magnet, right? We have a magnet here. Here we have current being supplied. So therefore, this is your current carrying conductor. Right? We have something called a commutator here or slip rings. Sorry, split rings. Right? Why we have split rings is that you see this coil here going to experience a force. And this part of the coil going to experience a force. So it's going to cause it to move. And when it moves, see this here? That will also move. Okay? Watch this here. So I'm going to let it run. See that? Watch how the rectangular coil in the middle moving and watch how the split rings moving. See that? You're seeing that? Yeah. Right? So that is your simple DC motor. Right? Current carrying conductor in a magnetic field experiencing a force. What we have to do as physics students is explain why it's moving like that. Okay? And then Fleming's left-hand rule is one of the most important things to explain what happened in there. All right? Let's see what we can see. What was the current direction? Right? If you look closely, the current moving in a clockwise direction. See that? Always moving clockwise. Yeah, fit. Say not. That's what your magnetic fields. So cutting magnetic fields there. And let's, okay, I don't want to show you the force. I want to just stop it here. A little bit again. Let's see if we can stop it in the middle. Woo. Oh, look at it up. All right. So here is what you have to do. You just learned about left hand rule, Christian. Right? You just learned about left hand rule. So I want you to use your knowledge of left hand rule to work out. Here's A, B, C, D. I want to know what's the force on AB, what direction is the force on AB, and what direction is the force on CD. What direction is the force on AB? What direction is the force on CD? So use Fleming's left hand rule. You don't have to draw it, just do it relative to the screen right there. Will AB experience an upward force or a downward force? Will CD experience an upward force or a downward force? Don't draw it, eh? All I want you to tell me is what AB will experience. Upward or downward? Huh? That's not. You work it out. I'm giving everybody a chance. AB is upward or downward? All right, let's go. AB is what? What you all got? AB is down, up. And CD is down, right? So Fleming's left hand rule, right? And based on the magnetic fields, north to south. All sure? AB is what? Down. AB is down. And CD is? AB is up, all sure? Magnetic fields north to south. Current direction is A to B. Are you sure? Or watch it again. Again down. Because the green line show you the magnetic field, right? Right? The green line showing you the magnetic field. The black arrow showing you current. So the force appears to be down. Watch it good. Huh? Look at the diagram. Look on the diagram. So we're trying to figure out on the diagram what direction AB will move in. Right? So watch it good. So here, magnetic field is north to south. Current going in. Stand up. The force is down. You'll stand up. Look at the black line. The black showing the black arrow.
Yeah.
Right, the arrow pointing A to B, and the magnetic field green line. So the force has to be downward.
Oh, yeah.
Fit? Trouble? Which one? Well, if you draw it, then you're going to be going kind of if you draw it, and you go, the way you look at there, it'll always looking upwards. But watch. Try to do it relative to that. So if I do the magnetic field here, and this going kind of up, this going kind of down. And by the treat it that way. Right? Right? So let's see if we write AB going down, CD going up. Let's let it run. See it? CD going up, AB going down. See that? Yes. So Fleming's left-hand rule helped us explain how it's going to turn. Any questions online? So let's put the force. See the force there? Right. Right. We have one slight problem, right? That black split ring, right? You see the black split ring touching the silver part? Right. When it touching the silver part, current will flow in the circuit. Right? But watch right here. When it like this, watch closely. It's not touching. It's not touching there. You all realize that? And if it's not touching, no current will flow. So then the laws can't apply. But why keep moving?
Because
Why just keep moving?
force.
Huh? Because of the force of the what? Of the motion of it. So what is called that? Something continuing to move although it's stuck. One of Newton's laws. It continues to move although same direction, although some unbalanced force. Inertia. Very good. Inertia. Very good, Elena. So because of inertia, it continues to move. All right. And once it continues to move, it will make contact, current will flow. Fleming's left-hand rule will be applied. Everybody okay with that? Why do they use split rings? Because split rings allow the current to continuously move anti-clockwise. Are you okay with that? Online? Are you okay with how the motor works? Anybody confused? So what we have to do now is to put this into our own words. Right? Nikolai, Haricharan, are you okay there? Selena, Baraj, Adelia, Adele, sorry. Right? So what we have to be able to do now is to take this motto and explain it in our own words. Right? I like to use an old past paper. Sorry, not old. But there is a past paper in push-ups. This thing upside down. Hold on, right? There's a past paper that gives you a few steps on how to answer it, and it's perfect. Okay, now that's not it. Oh gosh, boy. Next week is online alone, right? Just for you. Next week is online alone. All right, yeah. I don't even know what you say. All right, so watch here earlier. Here's an example of a question in a past paper, and they ask you to explain how the motor works. But the reason that I really like this example is it gives you a few pointers for you to learn and the order in which they explain it. So here's what you're doing. Your answer should include direction of current. So that's the first thing you do. Number two, forces applied and any rules. What's the rule you're using? Fleming's left-hand rule. The only thing they're missing is that you should label it. But this question already labeled it for you. Okay? Next thing, give you direction of the rotation. And last thing, how continuous rotation is achieved. So once you explain those things in that order, 1, 2, 3, 4, 5, that's full marks. Okay, full marks on how to on being able to explain the motto. So here's what you're gonna do from now. I want you to draw that and write down the 5 steps somewhere here. What here to do? You could draw it simple, just draw a block. Let's draw a block. Watch. This is the simplified version. This is the I cannot draw too good version. Right? So if you like Ravi and I can't draw too good,
Yes.
right? You could draw that version there.
So, yes, right. So I really think the class is right today. You know, I support that strong.
All right, we will see. You see, but it's our class after this.
They do we could settle on the one day after.
Yes, we will see. What's that? What is it?
Couldn't make up the.
Right, and I want you to now draw these write down these steps, please. Step number 1, label a diagram, which you can know already. Step number 1, label a diagram. Step number 2, exactly what you see in there. Give you direction of current, write it down all of, write down the steps, please. Step number 1, label diagram, A, B, C, D. Step number 2, give you direction of current. Step number 3, find the forces acting and steady rule applied. Step number 3 now. 4 give you direction of rotation. Step number 4 give you direction of rotation. And step number 5, how is continuous rotation? How is continuous rotation achieved? All right, right there. Write it down. All of them write this a little paragraph that is not this thing here. Same thing right here. 1, 2, 3. All of them right there. All right. So write down the steps. So now you hear the information. You're not going on your phone clearly. You're going to try to write it out. Hurry up. Sorry. Right? So I want you to try to write it in your own words. And I'll listen to it tomorrow. Yeah? So write it out. What direction current moving in? What direction the forces, if it moving clockwise or anti-clockwise, and then how continuous motion is applied. Right? Do that for me, please. Christian, work on that for me, please. You asking mom for me? That's up. If you're going straight home. Oh, that picking up. Okay. I'll have to wait now after rush. Come on, hurry up. What? Hurry up, hurry up. Answer number 1. Try and answer number 1. Label the diagram. Did you the diagram label? Yes. You have A, B, C, D, right? Step number 2. Step number 2. What's the current direction? What's the current direction? Current moves from the positive to the negative, right? So on your diagram, label positive and negative. Positive, negative. Okay, oh wait. The one I drew for you, I said put it around. Oh no. And same thing, right? Nice. Positive, negative. So current moving from D to C back down to A. So current moving in a what? Anti-clockwise. Nice. So current moving in an anti-clockwise direction. Now, use your Fleming's left-hand rule. Use your Fleming's left-hand rule and try to determine what's the force on AB and what's the force on BC. All right, so current moving here, here. Right, so we said current moving anti-clockwise. Work out the forces. AB is what? Up or down? What you all got for AB online? The force on AB, Hytran. The force on AB, up or down? Right, use your book, right? Use your book. Based on how you drew it. And you're getting what? Down? Are you sure? Yeah, down. north to south, based on what I have here in my diagram, magnetic field moving north to south, current coming from B to A, so I got up and then down here. Okay? Check in your diagram and see, right? So that will cause it to turn clockwise.
Yes, sir.
So that will cause it to turn in a clockwise direction.
It's all right.
Huh? So that'll be clockwise, right? So that will cause it to move in a clockwise direction. And what's the law we used? And we use Fleming's left hand. Jacob, make sure you can read this out to me after. I'll be writing this down. Right? And the law we use is Fleming's left hand rule. Okay? Which one? When we do generator. This right hand rule, we're going to use this when we're doing generator. This one? Well, that's the one from yesterday, from Tuesday. Yeah. This is grip rule and this is Fleming's right hand rule. All right. So we said it moving clockwise based on Fleming's left hand rule. How does it achieve continuous motion? Because when the coil is in a vertical, write this one down, I'll call this one over here. When the coil is in a vertical position, when the coil is in a vertical position, when the coil is in a vertical position, no current flows. No current flows. But because of inertia, it continues to move in the same direction. Right? Note that, last thing, note that the split rings or commutator, note that the split rings or commutator allows current to flow in the same direction in the coil. Note that the commutator allows current to flow in the same direction in the coil. Okay, that's it. That's the explanation. You don't have to learn to generate an SC. Learn to put it in point form. Number one, label. Number two, direction. Number three, force. Number four, and so on, right? Okay. So next day we will re-explain. I'll ask somebody to re-explain the motopoma, and then we will move into the generator. Oh wait, no, homework. Thanks for my mind, Jacob. Right? Thanks, Jacob. The loudspeaker. I want you to draw. Write this down for homework. Draw a simple loudspeaker and explain how it works. Draw a simple loudspeaker and explain how it works. Thanks, Jacob. Thanks for being in the class. All right, simple loudspeaker.